Hi, so we're going to do some fundamental practice for the relationships, common prefixes, and just beginning common concepts of circuits and basic linear circuits. So I'm going to start here with on the worksheet. We'll start with the relationships between different circuit elements. So the first circuit element we're going to introduce is called what you've probably heard is a volt or voltage. So a volt could be usually represented with if we know Ohm's law is V equals IR, which is current times resistance. We get current in amps times our resistance in ohms. So volts are also equal to amps times ohms, but they're equal to some more things, and that can be derived from different equations and other relationships. So another relationship is going to be deal with power, and we'll have watts over amps, and that'll be derived from our power formulas. And then we also have joules over coulombs, C. And lastly, this one you might not use that much, but it is important to know, is Webers over seconds. And we want to, if you don't remember, a Weber is magnetic flux. So Weber is going to be our magnetic flux, which will come into play later. That's more of a physics 2 concept, if you remember doing that. So the next one we have are amps or amperes. And an ampere is when we're dealing with current. Now that's going to be volts over ohms, which goes back to our basic relationship we have with Ohm's law. So I equals V over R, which would be volts over a resistance in ohms. Next, we go back to another relationship that kind of goes back to our voltage, and we'll have coulombs over seconds. That's a good one to know as well, and is usually used in the opposite sense, which we'll get to later when solving for coulombs. Or next, actually, that's where I'll go to. We'll go to our coulombs. This is more of this comes into play in circuits, but was originally introduced in physics 2. So a coulomb turns out to be a joule over a second. And alternatively, which can be written from here, is an ampere times a second. This one will come into play more. We'll notice this a little bit more. Then we can go to let's go to more of a power things. So we can go to watts. So a watt is equal to a volt times an amp. If you remember power in watts, or power is IV or VI, which is going to be your voltage times your current. So volts times amps. It's also equal to a, oh, excuse me, I made an error here. Coulombs is not joules per second. Coulombs is going to be joules per volt. My apologies. And that's because a watt is a joule per second. It's over time. So and this is the one you'll notice most when we're talking about watts. It's usually, as I've seen, joules per second or joules over seconds. Also known as Newton meters per second. And going back to our power formulas, V squared over ohms over a resistance, which, keep going, amperes squared times a resistance, right? V squared over R, and then I squared times R. Now we can continue with this. I'll jump up here, joules, and this will be closely related in that sense, will be watts times seconds. You can derive from here. You can multiply the S and divide the watts. Sorry. And we can also do coulombs times volts, or also Newton meters. And sorry, and that's what I was getting at here, Newton meters, joules. So this is joules over seconds equals a watt. So multiply a second over and we'll get joules. I was one step ahead in what I was saying there. Then we go back to a couple other basic ones related, like volts and amps. We'll get to ohms, used with resistance, and the conjugate Siemens. So an ohm is volts over amps, back to our Ohm's law relationship, V equals IR. And then alternatively, and why I have ohms and Siemens here, is back to our concept of duality. So if you know that resistance and conductance are duals of each other, and the units of resistance and conductance respectively are ohms and Siemens. So Siemens will be amps over volts. And then we could continue with ohms, which would be 1 over a Siemens, which, keep in mind, this is a capital S, okay? A lowercase s is going to equal what we've seen all the time, seconds. And then back to Siemens, this same relationship is going to be 1 over ohms, 1 over a resistance. Now, lastly, we have 2 more that won't come into play right now because we're not really dealing with capacitors and inductors, but they may come into play, and it's good to know, is farads and henries. This is also another physics 2 topic that we're coming back to. So a farad is coulombs over volts, seconds over ohms. The one we're going to see, I've seen a little more often, is amperes times seconds over volts. And in relation to henries, and it's good to build a relationship there, it's going to be seconds squared over henries. Henry, let's start back at the seconds, the second squared. So alternatively, henries is going to be seconds squared over farads. We have ohms times seconds. With this relationship, we would have volts times seconds over amps. And the last one that may prove important to us is going to be joules over amps squared. So these are the basic relationships I would pay attention to, and I would know. There are more, and you could make more relationships out of these, and I would encourage you to do so. But this is a good start to understanding those relationships. So the next thing I have down is we're going to do some common prefix and relationship calculations to understand how we have the prefixes such as milli, kilo, femto, atto, deci, centi, understanding those. We will more deal with the kilo, mega kind of units. So we'll begin with our first one here, which I'll fold my page. The first one I have here that we can look at is going to be 5 milliamps times 3 kilovolts. Little k, even though kilo is, as we'll get to, is positive, a positive factor power, it is a lowercase k, uppercase Kelvin. So we have 5 milliamps times 3 kilovolts. You could multiply this out and get a number, or what I choose to do and what I'm going to do for my method showing here is I do it in my calculations. So, and I'll explain what I mean by doing this. So we have 5 milliamps. Milli is going to be times 10 to the negative 3. So we have 5 times 10 to the negative 3 amps. The 10 to the negative 3 is the milli, or milli. And we're going to multiply that by 3 kilovolts, which is going to be 3 times 10 to the 3, positive 3 volts. Awesome. So now we can multiply the 5 and 3. We'll get 15. And then we have 10 to the negative 3 and 10 to the positive 3. If you remember your relationships of exponents, if we had 10 to the 4 times 10 to the 6, we get 10 to the 10. They add, they do not multiply. If we had 10 to the 4 to the 6, right, we would get 10 to the 24. We had 10 to the 6 over 10 to the 4, we get 10 squared. So that's going to be the relationship we have there. So we have negative 3 times 10 to the negative 3 times 10 to the positive 3 is going to give us 10 to the 0, or 1. So we're going to have 15 times 1. And since I multiplied the milli and kilo out, we just have amps times volts. If we go back to our relationships, and maybe you'll have them down, we'll see amps times volts is watts. It's power. As we'll see in our power relationship being V times I. So we have volts times voltage times current. So we'll have 15 watts of power. And now we can go to number 2. This is going to be 0.5 megawatts, capital M. Important to note the capital, times 20 seconds. I'll let you work it out real quick, see if you can come to it. Feel free to pause the video. I'll wait another 2 seconds. And here we go. So 0.5 megawatts. Mega is a factor of 10 to the 6. So we have 0.5 times 10 to the 6 watts times 20 seconds. Seconds doesn't have any prefix, so we'll just keep it as seconds. So we have 0.5 times 20 is going to be 10. And then we have 10 to the 6 times nothing is going to be times 10 to the 6. And watts times seconds is going to give us joules. And now this is also equivalent. We want to keep going. We don't want to just leave it there. We know what 10 to the 6 is because we just used it in this problem. And 10 to the 6 is mega. So we have 10 megajoules. MJ. Capital M. Remember that capital is important. Number 3 we'll do. So we have 13 milliamps times 26 volts. Take a second, wait. And we'll go for 13 times 10 to the negative 3. We have milli. So 10 to the 3 amps. I like keeping my units, keep the units going through the whole process. That way we know, especially when you're going around circuits, if you're solving for a current and you start multiplying, so you want current and you multiply volts times ohms, you did something wrong, because a volt times an ohm does not equal an amp. So then we also have 26 volts. That has no prefix on it. So we'll stick here at 26. And that'll give us 13 times 26, which is going to be 338 times 10 to the negative 3. And we have volts times amps. So we get something we've already used before at the very beginning. We have amps, volts, amps, same thing. And we'll get watts. Now, we also have one more step to do. 10 to the negative 3 is milli. So we have 338 milliwatts of power. So we'll go to number 4. Keep going along here. So number 4 is going to be something new. We're going to do division. So back to division. We can look back here. Division right here subtracts. Okay. So we have 4. We have 40 microjoules. That's what mu is micro, over 25 kilovolts. This will actually, it looks a little weird, but it's actually going to give us something really interesting, something very cool to look at. So we have 40 times 10 to the negative 6 divided by 25 times 10 to the 3. So 40 over 25 is going to give us 1.6. And we have 10 to the negative 6 minus 10 to the 3. So negative 6 minus 3 is plus a negative 3. So we're going to have times 10 to the negative 9. Let me make sure I'm doing this correct for this one. Correct. Awesome. And we also have, so now we have, excuse me for not carrying my units, we're going to have joules over volts. Now, joules over volts gives us something that we also had when we went over at the beginning. And that's going to give us coulombs. It's going to give us a unit of charge. So we have 1.6 times 10 to the negative 9 coulombs. Times 10 to the negative 9 is one we haven't used yet, but it's one you may use, and you've probably heard, if you've ever heard of nanotechnology, is nano, 10 to the negative 9. So we have 1.6 nanocoulombs, lowercase n, uppercase C. 5. We have 50 milliseconds. And 45 gigaamps. Giga, something really cool. If you're into computers at all, you heard gigahertz. This is also the same thing. Well, the same idea of giga. So we have 50 milliseconds. 50 times 10 to the negative 3 seconds. And we have 45 giga. Giga is going to be like nano. It's the opposite, though. It's going to be times 10 to the 9, positive 9 amps. So we're going to have 45 times 50, which is 2,250 times 10 to the 9 plus negative 3, or negative 3 plus 9. is going to be 6. And we have amps times seconds. So amps times seconds is going to give us something interesting as well, and actually something we just did, but also shows you the relationships between these variables, between these units. Is a joule over a volt is a coulomb, but an ampere times a second is also a coulomb. So we have 2,250 times 10 to the 6 coulombs. Or if we say we move this, so we move it 1, 2, 3 places. So that's going to be 10 to the 9. So this is also 2.25 gigacoulombs. And what I meant by giga when I was talking about, if you've ever heard of a processor, it runs at 4.2 overclocks to 4.2 gigahertz. That's 4.2 times 10 to the 9 hertz. So, number 6, keep going. We'll have, excuse me, 33 microamps. Sorry, excuse me, microseconds times 0.4 teravolts. Tera, that's also a new one we haven't quite gotten to yet. And we'll do here in a second. So give it a try. Awesome. So Tera is, if you've ever been working with memory on a computer like Giga, we have 33 microseconds. So we'll have 33 times 10 to the negative 6 seconds times 0.4 times 10 to the 12 volts. And what I meant by storage is you have a gigabyte of storage versus a terabyte of storage. Terabyte is that one step larger if you're going to buy it. So we'll have 33 times 0.4, which is going to give us 13.2. And we have 12, or 10 to the 12 times 10 to the negative 6. So we'll have 12 plus negative 6 plus 12 is going to give us 6 times 10 to the 6. And we have volts times seconds. So if we look, do we have anything that kind of represents volts times seconds anywhere? Let's think for a second. And yes, we do. We have amps. So, excuse me, making sure. Oh, that's, I messed up here, my bad. It's not, I didn't mean, so we got the tera. I meant, it was supposed to be terawebers. Sorry. So volts times seconds is Weber. So we'll have 13.2 times 10 to the 6 Webers, which is going to be equal 13.2 megawebers. It's kind of cool. My apologies for that. I looked at it wrong. Number 7. So number 7 is going to be 72 kilowatts over 18 megavolts. So back to division, we have something new again. We're going to have 72 times 10 to the positive 3 watts over 18 times 10 to the 6 volts. So we have 72 over 18, which is going to give us 4. And we have 10 to the 3 over 10 to the 6. So we're going to have 3 minus 6. The order on this one does matter. So 3 minus 6 is negative 3. So we have times 10 to the negative 3. Watts over volts. Think for a second. What does watts over volts give us? It's going to give us amps. So we have 4 times 10 to the negative 3 amps. It's going to give us 4 milliamps. 8. Move it up a little. We are back to another division. So we're going to have 42 milliseconds over 6 kilo ohms. Again, try it on your own. And now we're back. 42 times 10 to the negative 3 seconds over 6 times 10 to the 3 ohms. 42 over 6 is 7. 10 to the negative 3 over 10 to the 3 is going to be negative 3 minus 3, which is going to be negative 3 plus a negative 3. So 10 to the negative 6. We have seconds. We're going to have seconds over ohms here, which is going to give us something new, something we already went over, though. It's going to give us farads. So we're going to have 7 microfarads times 10 to the negative 6 is micro. Remember mu? Mu here is micro. And now number 9. Almost getting to the end of our division. And the end of these. So number 9 is going to be something a little strange for this one. It's going to be 18 millivolts times 2 seconds over 3 kiloamps. Now this is odd because we have 3 in here. We have volts times seconds over amps. So I'll give you a second. So the hard part here is not necessarily going to be the math if you've been doing well so far. The hard part here is going to be figuring out what units this is going to end up in. So I will go now. 18 times 10 to the negative 3 volts times 2 seconds over 3 kiloamps is going to be 3 times 10 to the 3 amps. And that's going to give us 18 times 2 over 3. So it's going to give us 36 over 3, which is going to give us 12. And now we have negative 3 seconds and over 10 to the 3. So think for a second. What would that give us? So we have negative 3. We just have regular 2 seconds, and we have 10 to the 3 on the bottom for amps. So the part here that you need to kind of look out for is the seconds. The seconds has a times 10 to the 0, so that won't add anything. And then we have negative 3 over 3. So we're going to have negative 3 plus a negative 3, negative 6. So we're going to have 12 times 10 to the negative 6. And the part we went over, we haven't gone over here, is something new. Amperes times seconds over volts. Sometimes it helps to write it out like this. And that gives us what we just worked with, farads. So we have 12 times 10 to the negative 6 farads, which equals 12 microfarads. And now we can go to number 10, which is gonna have to move my page. Number 10, which, let me pull it up, is 27, something new, femtoamps over 3 microvolts. Femto, Give you a second. Femto is times 10 to the negative 15 times 10 to the negative 15 amps over 3 times 10 to the negative 6 micro. We've already gone over that. Volts. We have amps over volts. So 27 over 3 is 9. Negative 15 minus negative 6 is going to be negative 15 plus 6, which is going to give us negative 9. So 9 times 10 to the negative 9 amps over volts. So what will amps over volts give us? It'll give us something new that we actually we haven't touched yet, except for what we did at the beginning. I'll give you a second. It gives us Siemens. If you remember, volts over amps will give us ohms. Therefore, amps over volts will give us the dual, which is Siemens. So 9 to the negative 9 times 10 to the negative 9 is going to be nano. So we have 9 nano Siemens, capital S. That capital S matters because if we had 9 and lowercase s, that would be 9 nanoseconds, which is also something we might deal with. So you need to be careful. Awesome. So that now concludes the common prefixes. So now we'll begin with the basic circuits and the addition of resistors. So we'll begin with this circuit, number 1. And we're going to have 3 resistors. And they're going to have the values 3 ohms, kilo ohms, 5 kilo ohms, and 7 kilo ohms. Now take a second to think, are these 3 resistors going to be in series, or are these 3 resistors going to be in parallel? Pay attention to the meshes and pay attention to the nodes. So when looking at the nodes, we're going to notice that this 3 kilo ohms is connected to this node right here. I'll name V1. And we have V2, V3, V4. So 7 is connected to 4 and 3. 5 is connected to 3 and 2. And 3 is connected to 2 and 1. So they're not really connected in parallel, right? Because none of them share. 7 isn't also connected to 2 and 3. And 3 kilo ohms isn't also connected to 2 and 3. So let's take a look at the meshes. So we have, say, our inner mesh going down here. And let's have an outer mesh going out here. And look, all 3 of them share the same 2 meshes. So we're going to say these 3 resistors are in series. Resistances in series combine, they add, it's the sum of all those resistances in series. So we're going to have our 3 kilo ohm resistor plus our 5 kilo ohm resistor plus our 7 kilo ohm resistor, all in series, giving us 15 kilo ohms total. Keep in mind the kilo ohms. 15 kilo ohms and 15 ohms are 2 very different resistances. So let's look at the second circuit. This one's a little different. You can solve it in 1 step, or we can do what I'm going to do is solve it in 2. So we have 3 resistors, and we got a little bit of a different configuration going there. So we have one here, 7 kilo ohms. We have a 2 kilo ohm, and I believe the bottom is a 3 kilo ohm. Oh, it's a 9 kilo ohm. My apologies. So we can look at the nodes and the meshes. I'll give you a second and pause the video. And we'll notice the 7 isn't really in anything yet. The 7 is not in series with the 2 or the 9. And it's not in parallel because this node is alone and they're not really, it's not connected to anything. But we can look at the 2 and the 9 and compare them. So let's compare their meshes just to see. So we got a mesh going this way. And we could have a mesh going around this way. And say there's one down here going that way. So we'll make that our outer mesh. We would have this mesh for the 9, and then we'd have this one for the 2. So they're not in series. But let's look at their nodes. So we got V1 is a node here, and V2, just arbitrary numbers. They're completely fictional. And we'll look in this node is connected to the 9, and then this node is also connected to the 9. They're both connected to V1 and V2. Therefore, these two resistors are in parallel. So with two resistors, we can find their equivalent resistance. It's going to be 2 kilo ohms times 9 kilo ohms over 2 kilo ohms plus 9 kilo ohms, which is going to give us 1.64 kilo ohms. And now we can redraw the circuit, and this is what I was saying. You could do it in 1 step or 2 steps. I'm going to do it in 2 just so we can visually see it. But if you're able to jump to this part in your head, that's awesome. And you could definitely do that. We have 7 kilo ohms and 1.64 kilo ohms. And these two, are they in parallel or series? I'm going to say these two are in series because we have a mesh here, or a mesh here, and a mesh up here, and they're both on they both share the same meshes, but they don't share the same nodes. So these two are in series, and resistances in series simply add. So we're going to have 7.7 kilo ohms plus 1.64 kilo ohms, which is going to give us 8.64 kilo ohms. So the equivalent resistance of that circuit is 8.64 kilo ohms. Oh, my apologies. 8.64 kilo ohms. So now we have 2 more circuits, and we're not going to be combining resistances in this one. Actually, we will, but that's we're adding something else into it. I'll draw the circuit, and we're going to have a voltage source here, and we have 4 volts with the positive facing up, positive on the upside. We have a resistor. We have another voltage source. We have 8 volts. And we have another resistance across here. And we have 4 mega ohms and 3 mega ohms. So take a second with this. So based off what we just did, we can look at these 2 resistors, and we know that they are not in parallel, right? The nodes, we have 4 nodes, but we have 2 meshes. We have an outer mesh, we can say goes this way, and then we have an inner mesh, we can say goes this way. So resistors in series add. Or we can do an equivalent circuit, and I'll draw over here. Doesn't matter where you put the resistor. I could put it over here. I could put it here. I could put it here. I could put it down here. It doesn't matter. For nice looks, I'm going to put it on the top. as long as it's still in series. We got rid of the combine. It could go down here, it could go up here. Mega ohms. They do combine. And then we have a 4-volt source and an 8-volt source. So now this is where we gotta think. So are these two voltage sources in series? In series, that's a very fundamental. They must be in, the voltage sources here must be in series. In parallel, it's either redundant or not allowed. It would be not cool. So in series, we have our 4 volts and 8 volts. So a good way to see if they're going to combine is I'm just going to draw my pencil through it. So we're going to go up and we're going to hit the negative, come out the positive. So we got a positive here. And we're going to keep going, and we come down and we hit a positive. Right here, we hit the positive. So we left a positive and we come into a positive. We start a negative and we come into a positive. So imagine this like you have batteries for your flashlight and you are trying to put them together like this. Is your flashlight going to turn on? No, it's not, because this is a positive and that's the positive. So we need head to tail. So following through this, we're going to end up with them not being the same same sense. So we could take the 8 volts. So say we're going around the loop this way. We'll use passive sign convention. We'll have negative 4 volts, the voltage rise, and we'll have positive 8. So we could do 7 mega ohms and 8 volts. Yeah, 8 volts, my bad. 8 minus 4 volts. So 4 volts. So now we have question 3. And this is going to be a dual of the one we just did. So we have 3 amps, 6 kilo ohms, 7 amps, and 5 kilo ohms. So let's look, and I just keep in mind, I just said it's the dual, so we just had a series circuit. So think of the dual of a series. These elements are going to be in parallel. So we can combine these parallel resistances. I'll do that here. So we can have 6 kilo ohms times 5 kilo ohms over 6 kilo ohms plus 5 kilo ohms. Awesome. So that'll give us 2.7273, we're rounding, kilo ohms. So I'm going to keep that resistor in the middle, just so you can see that they're still going to be in parallel. So we can redraw our circuit, keep the sense of the currents the same. 7 amps, 3 amps. So now, and also we have 2.73 kilo ohms. So now we can look at these current sources. And we're going to analyze these just barely different than the voltage sources. So the voltage sources we just followed around and we saw enter, exit. Here with the current sources, we're going to look at the sense of the current. And what we could do, how we could do that, is we can look from a shared surface. So we can either look from here or here, and we can see if they're entering or exiting together. So from this node, we can see that 3 amps goes this way. And we can see that the 7 amps also goes the same way. So they do share the same sense. Them sharing the same sense means they're going to add. Looking at it from this way, that goes that way. Looking at it in, that goes the same way. So, and I'm going to show you how some people go and do what you try to do with the voltage. So if you go in through here, all right, so arrows this way, this way. Oh man, sorry, this way, this way, this way, that one. Oh man, that's the wrong way. That's the wrong direction. And then you'll think that they're going to subtract. But no, they actually add because they have the same sense going upwards. So we can redraw this, and they're going to add. And we could add them over here or over there. I'm going to keep it on the 7th side. So we'll have our resistor, our current source, 10 amps. And this is 2.73 kilo ohms. And that is our final circuit.